Hello everyone and welcome to the 7th tutorial of Introduction to Deep Learning for this semester. Today we will talk about exercise 6 that you have submitted. We will talk about deep learning frameworks, and we will present exercise 7 that you have to do this week. Finally, we'll talk about the exam, and we'll give some details that all of you have been waiting for. So you submitted exercise 6 successfully, most of you. We were happy to see many submissions, and some of them even got really good scores. There was already one question in Piazza about this one submission that got 82% accuracy. So I can reassure you, this submission, we looked at the code, and the person who submitted this model, they just copied an implementation of convolutions, and that's why they were able to achieve a much better score. But all the submissions below this one are basically submissions that you could have achieved with proper tuning of hyperparameters and some other tricks that some of these students have used, and we will talk about these. Of course, if you look online and you look at the leaderboard for the Cypher 10 dataset, you see that we have reached a point where it's basically solved. EfficientNet gets 99.7% of accuracy, and the biggest secret of how this is done. So there's a lot of optimization there of the techniques and the hyperparameters, but one big thing that you were missing in this exercise is actually convolutions. Since you were only doing few layers with linear layers in between them, then you are bound to not get such good accuracy as you see here. So there's still a way to go, but there is a lot of simple stuff that you can do to get there. For example, if we look at the code from one of the students, they used transformations on the data. So you can call it data augmentation, and what they did here in the notebook, you can see, and they even visualized it. They load the images and then just add random noise. So they call this salt pepper noise. And with some probability, you add white or black pixels. And they did other transformations, such as random rolls, where they just shift the image by a few pixels. And they also do, for example, another kind of noise where they add colored noise, and all these, they augment the data set with all these images, and in turn it improves the network's performance on new data. And that's how you can get better scores even with those same networks. So here you can see also the hyperparameters that the student used. So they have the probabilities that they had for each kind of noise, and they used a hidden size of 258, some regularization coefficient that they found, and 3 layers. And they were able to get 57 or 58% to this one. So what else is stopping us from getting to these scores? One is something that some of you have already encountered. It's just the lack of computational power. So you were training it on your own machine. You did not have a big cluster of computers to compute this on. You did not use GPUs, and you just simply cannot run so many experiments to just find the best hyperparameters and squeeze the loss percentage of accuracy like they do on these leaderboards here, where each one is usually an academic paper that introduces some novelty. As I said earlier, there's the architecture here where we're using very simple linear layers with activations in between. CNN should give you a good boost, so we will be using convolutional neural networks in the future exercises. And one more thing is the initialization of the weights of the network. You've already seen that in the lecture. It is relevant especially for deeper layers, it turns out, and especially if you use ReLUs, that initialization matters, and just choosing randomly is not always the best choice. I'm pretty sure there was also at least one student who implemented Javier initialization as well. So that should help you train deeper networks and get better gradients. So that's what I wanted to say for this exercise. And now we can talk about the deep learning frameworks. So the two famous ones are, of course, TensorFlow by Google and Pytorch from Facebook. But there are many other frameworks as well for deep learning. And they mostly differ in how they handle the compute graph. So as you've seen in exercise 5, we can break down all the operations we do into little layers, and for each layer you have forward and backwards function. Now, if you have the entire compute graph and you know what all the operations that you're going to do, then you can easily just change the order and from forwards to the backwards pass by using the chain rule and the backwards function of every layer that you have in the compute graph. And there are two approaches for this. So TensorFlow takes a more static approach, and with TensorFlow you traditionally need to know the entire compute graph ahead of time and all the operations and the parameters and the loss functions that you're going to be using, and it compiles the entire graph, so it knows what the backwards pass will be, and it just has to kind of plug in the numbers there. Pytorch, however, takes a much more dynamic approach, similar to how Python works. If you compare TensorFlow to a more compiled language, and it just computes the computational graph dynamically in runtime. So this results in Pytorch code being slightly easier to write, in our opinion, and that's why we also choose Pytorch for the exercise here. And I would probably say that in the research community, more people tend to use Pytorch now. However, recently TensorFlow also has this eager execution mode, which behaves more like Pytorch. So yeah, in industry, maybe people prefer using TensorFlow, but for us, Pytorch is great. So that's what we'll be using. Of course, you don't have to lock yourselves to one option. Converting between the representations, or you can always develop something in one framework and then just convert it to another framework. In the end, what you have is just weights, right? You just have to make it work in the other framework. So if we dive deeper into Pytorch, we have these three pillars of deep learning that we were talking about earlier in the tutorial sessions. And Torch basically has them all here. And so we had the data set, and data loader. And in Pytorch, you can simply find it in Torch utils, Torch datasets, and Torch vision transforms. And they have all the functions that you need to load data and do transformations and images and so on. And then for the model and the loss functions, you have everything you need here. And then for optimizers, to solve for the model parameters, you have Torch Optim that has all the algorithms you will need for optimization of neural networks. Yeah, so one more thing that Torch handles really nicely for us is GPU support. So if you're working on a machine that has a GPU, it's very easy to just let Pytorch know that you wanted to use the GPU. So if you have a GPU, you just do CUDA 0. If not, you just choose CPU. And this is something we also show you in the notebook. So if you just follow the notebook, that should be clear to you, how to use your GPUs. As I said, Torch Vision has packages to handle datasets. It has already support for all the famous datasets such as MNIST, Fashion, MNIST, ImageNet, and so on. And you can just load them with a single line of code here. And if you try to actually build a neural network in Pytorch, then the basic structure is something like this. So you import Torch, and NN stands for neural networks, and this is NN module is the base class, and this is what a very simple network looks like. So here you have the initialization, and you just initialize a fully connected layer here. So you can find the layers in NN. So we take a linear layer from NN, and here you specify the sizes. And then, of course, you have the forward pass. You tell the network what to do with the input it's getting. So we're just taking the input x and putting it through our linear layer, and we're just returning that. And this is how you call the net. And you do net.toDevice to put it on your GPU if you're using a GPU. One thing you might ask yourselves is, where is the backward pass? So that's the nice thing about Pytorch. You don't have to write the backwards function here. So when we were implementing it ourselves, we of course needed to do that. But the whole point of using Pytorch is this auto differentiation, and that basically every operation you do here, it already has a coded backward function. So you don't have to take care of it. Pretty much everything you do is taken care of. And when you just call backward on the final loss value that you have, then it all happens automatically. And that is really nice. Of course, if you do write your custom layers or custom losses, then you might have to implement the backward pass for them. And that you have to do on your own. And that's where your knowledge comes in. So that is all for Pytorch. There are some references for you here that you can use, and of course do the notebook. That should help understanding it. The next topic I'd like to talk about is visualization. So until now we were just plotting our loss curves in the notebooks as line curves basically. And now we want to step up our game, so we will start using Tensorboard. And the name might suggest it, but Tensorboard is actually a package from TensorFlow, but it was just very successful, and it's found its way into Pytorch as well. It's very widely used, and it allows you to visualize a wide array of visual data, such as plots, images, even 3D geometry that you need to visualize for the training and understanding of your network's performance and the training process. It's very easy to use, and that's why it's so popular. So we'll be using this in the notebooks as well. It can even visualize the structure of the network for you. Of course, when you do it with Pytorch, then you have to do one forward pass of the network, because there is no compiler, so it doesn't know yet what the network structure would look like. But if you do this one forward pass, then you can already get this visualization of your network and its layers. And as I said, it has many kinds of visualizations. Here you're seeing fashion MNIST images. Here you're seeing these graphs that show what happens with different initializations and different layers throughout the network. And our goal is that you feel comfortable to use all these types of visualizations and do as much of them as possible, because the more you look at your network, the more you typically understand it. And one nice thing is that everything is saved automatically when you log it into Tensorboard, so you can always access it in hindsight and also in this temporal manner. So as you train, you can see the different images that were generated. Yeah, this is what you talked about in the lecture, where you saw how the weight initialization matters. So previously in the lecture you saw this graph, but if you actually do it in Tensorboard, then you can see something like this, which looks nicer. The next thing I'd like to talk about is Pytorch Lightning. This is something that you can use on top of Pytorch. You don't have to. And the idea behind it is that there is a lot of code that every project in deep learning needs, which is, for example, loading the data and having this loop that loops over your epochs, or the data set and feeds it to the model and does the backwards steps and logs everything and saves the model, and it ends up being quite a lot of code that's not actually the core thing here, and you just end up copying it from one project to another. So the idea behind Pytorch Lightning is to do this automatically and just focus on the main thing, which is the model and the loss function, basically. So that's what they call the research code, and they call it Lightning module. And then you have the engineering code, which is the code that you don't want to write, and that's the trainer. And you have the rest, which is, for example, logging and organizing the runs and saving your checkpoints. And that's done through callbacks. So what it looks like in practice. So on the left here, we have Pytorch code. So you just have here a model with 2 layers. If you look at this net class, and then you have a typical loader for the data set and the data loader. And then you just have this loop for epochs that takes the data, loads it into the network, puts it through the network, computes the loss, does the backward pass, and does an optimizer step, and then writes out the loss values. And what happens with Pytorch Lightning is that everything that's in a box here is implemented as functions that you as a user have to implement. So you always have to define the Lightning module. You have to implement the train data loader, so it knows which data to use and how to load it. You have to implement configure optimizers to tell it which optimizers to use and what parameters it's optimizing. And most importantly, you implement this function training step, which just says what happens in every step of the training. But all the rest, everything that's in blue here, is just happening automatically here with this trainer clause from Pytorch Lightning. And you don't have to do that, and that's quite nice. So everything happens by just calling the trainer and calling the fit function. So like every library that abstracts things from you, there's advantages and disadvantages to Pytorch Lightning. Of course, it enforces a really nice code structure for your project. It's very readable. It's nice for debugging. You already get all the logging done nicely. It works automatically with some other stuff like weights and biases if you want to use it. And of course, there can be problems, right? Because the less you implement or the less code you see, the less you know what's going on behind the scenes. And if there is a problem or a bug, then it's harder to find. And also, if you want behavior that's not the textbook use case, then of course you sometimes deviate, and it's harder when you're constrained by this library. So it's more your decision whether you want to use it or not, but it's definitely worth giving it a shot. So your tasks for this week is to go over all the notebooks. So as I said previously, there is no mandatory submission this week, but there are notebooks, and you should definitely go through them because you will need to know how to use Pytorch in the next weeks if you want to submit the next exercises. They will all be in Pytorch. Pytorch Lightning is not a must, as I said. It also works regardless whether you submit a Pytorch Lightning module or just a normal Pytorch module. because they implement the same base class. So it's your choice completely. And just play around with it. Also, Pytorch has really nice documentation online. I find it super user-friendly, and I always use it in my daily work in research. They have a user-friendly one, but it's also very easy to look at the code. And the code is also super well documented. And some of the stuff will already look familiar because the way we implemented our NumPy stuff is already quite similar to how Pytorch does it to start with. So you are able to submit this week the same exercise as last week, basically the CIFAR 10 dataset classification task. There will be another leaderboard and an open submission. And now you can basically use Pytorch to do so. And you should be able to get better models. You have much more options, much more stuff to play around with. And we expect you to do that, but please don't use convolutional layers just yet. The goal here is that you use other stuff that Pytorch has, like, for example, data transformations and data augmentation, or different initializations or dropout, or other stuff that you think might help. But yeah, please try to stick to fully connected layers at this point. And of course, use Piazza as usual. If you have any insights that you want to share with your colleagues, it might help them and form discussions about it. All right, so last but not least, we have the exam to talk about. Many of you have been waiting for the details about the exam. We finally know the date of the exam. It will be July 13th. We already know that this clashes with another lecture, cloud computing. There is nothing we personally, the I2DL staff, can do about it. You are free to contact the examination board, which is who decides on the dates of the examinations. I hope they find a solution for you. The exam will be online, and that means you will have to be at home with camera supervision. We don't know all the details yet about how we're going to do this, but most likely it will be similar to last semester. That ended up working fine. What we had last semester was many big blue button rooms. It's a platform that TUM uses. So you're assigned to a room, and each room has a supervisor, and you set up your cameras behind you such that the supervisor is able to see your desk, what you're doing, and your screen, your computer screen. And this way we can see that you're just writing the exam and not looking online or not looking at the lecture slides to find the answers. Of course, it's not the easiest thing to have a camera behind you if you're using a laptop or something, because the camera is always here. A camera in front of your face doesn't really help us much. What many students did last semester was just log into BBB with their smartphones and just place the smartphones behind them. That worked fine. And then at the end of the exam, you have to scan the exam that you wrote. So you take your phone and you use some scanning app and you scan it and then upload it to wherever we tell you to. And during the time where you upload it, you're also supervised because you're still logged in from your other computer or your single computer with a webcam. So this way you're supervised the entire time of the exam. That's, of course, it's not ideal, we know that, but that's the only way we see possible with the current situation. You probably have many questions about it, or many personal questions, like I don't have a webcam. You can borrow one from RPG. You have to email them, and if you come with a student card, they can give you a webcam. We don't have all the details yet of how the supervision will be exactly. Be sure that we will publish it in due time. I think it's only 7th week, so there's still time for that. Yeah, but once we know all the details, we will let you know. And as for the content of the exam, first thing, you already have a mock exam uploaded onto the course webpage. You can have a look at that. The exam typically has a few different sections. The first section is always multiple choice questions that consists less than 20% of the exam. And then you have a bunch of short open questions where we ask you short questions. They could be theoretical or practical, and you answer in a sentence or a few sentences or a very short mathematical formulation. And then there's a few questions with a few parts, and you have to answer them with longer answers, and you have different parts of the question depending on the previous ones. All right. One more thing I want to say, it's not related to the exam, but I think sometime in the near future, the faculty will be sending a survey regarding the courses. So we ask you to please take the time to fill it in. It will help us know what we do well and what we could do better. So it would be great if you fill that. So to summarize today, on Monday you should be watching lecture number 8 about training neural networks. There's no mandatory exercise submission on Wednesday. So yeah, enjoy the nice weather on the weekend. And then next Thursday we have tutorial 8 where we talk about autoencoders. All right, thanks for watching.